Thank you. Yes, I present this work, Understanding of Linear Operators through Wigner Analysis, which will be a generalization of the previous work, which was presented by Professor Elena Cordero. And we will consider Schrödinger problems with a different perturbation, which has symbols in modulation spaces. So this is a joint project with Elena Cordero and Gianluca Giacchi. And let me give you a quick review about the preliminaries for those who were not here before Elena's talk. And we have a Wigner distribution with Fg in L2. And when F is equals to G, we call it W of F. And the original idea by Wigner was to consider, given an operator, a linear continuous operator on L2, was to consider another operator, capital K, which satisfies this interwinting relation. So as the title says, we want to study linear operators through Wigner analysis. So we have a linear operators T on L2 over D, and we use the Wigner distribution to pass to the time frequency space. And at the time frequency level, we have the operator capital K. The integral kernel of K will be called the Wigner kernel of T. Here we have some historical review about this kind of studies. The first work was by Wigner in 1932, where he first introduced the Wigner distribution in his work about quantum thermodynamics. And our focus here is to study Schrödinger type propagator with Hamiltonian given by a quantization of a quadratic form time plus a perturbation with symbol in modulation space. So here we have the problem, which is similar to the one discussed before, but I underline the fact that now the perturbation has symbol in the modulation space M infinity Q with Q between 0 and 1. So we are in the quasi-Banach setting, and even differentiability may fail because before we had symbols in Hormander class, and now we are working on in a more general context of modulation spaces. Some examples, we have the free particle and harmonic oscillator where the perturbation is 0, and a more generic Hamiltonian with perturbation with symbol in modulation space. Again, let me give you preliminaries on phi of type 1. For integral operators of type 1, we have a quadratic phase with this canonical transformation S, which is a symplectic matrix with this block decomposition, and with symbol now in modulation spaces M infinity Q. So this is the action on a generical Schwarz function, and the integral, of course, is to be understood in a weak sense. Particular instances of fields of type 1 are pseudo-differential operator which can be obtained by choosing the quadratic phase phi of x psi equals to x times psi. So the integral kernel of this pseudo-differential operator is given by this formula where we are acting on the symbol sigma with a partial Fourier transform with respect to the second variable, composed with a linear change of variables. We have an important algebra property of this operator. So take sigma and tau with symbol in M infinity Q of R2D. And then we have that they are bounded linear operators on L2 in the sense that they are acting on a Schwarz function, and the image will be a L2 function, and we can extend them by density on all L2. So The second property is that if you compose two pseudo-differential operators, you obtain again another pseudo-differential operator with a symbol in the same class. And also, if sigma is invertible, the inverse is again a pseudo-differential operator. So they form a Wigner subalgebra of B of L2 over D. We were studying a Schrödinger problem with Hamiltonian given by a quantization of a quadratic form and plus a perturbation with a symbol in M infinity Q. And if the quadratic form, which can be written this way with BC symmetric matrices, the classical evolution of the system is described by this Hamiltonian system, and the Hamiltonian matrix associated to the system is given by this block decomposition. It belongs to the symplectic Lie algebra. Here you find the definition of symplectic Lie algebra. And the solution of the classical problem is at every time t symplectic diffeomorphism. And this symplectic diffeomorphism can be obtained as the exponential of t times the Hamiltonian matrix S, and it has this block decomposition, and by explicitly writing the exponential with its power expansion, you obtain that the upper block AT is invertible for t between a certain minus sine t and sine t. And here I present some explicit calculation with the free particle, where everything works fine. And we have a representation of Schrödinger propagators, as we said before, as Fourier integral operators of type 1 at every time t. But this is not the case of the, for example, anisotropic harmonic oscillator. I just wanted to present another example different from the previous one. Here we see that at this particular instance, we don't have the representation as Fourier integral operators of type 1. So we search for a new classes of operators, and we define a new class of operators, and we discover that propagators will join this class property. But first, let me give the rigorous definition of Wigner kernel of a linear continuous operator from S to S prime. This is the operator satisfying this interwinding relation with T, with a cross Wigner, so not only with a Wigner of F, but with a cross Wigner. And it can be proved that capital K exists and it is unique, and just by testing it on this kind of Schwarz function, you obtain the existence of the well definition of capital K, because the linear span of this subspace of us as R2D is dense in as the Schwarz class on R2D. So the integral kernel of this capital K will be called the Wigner kernel of T, and for example, we can relate the Wigner kernel of T with the Schwarz kernel of T, or integral kernel of T, by this relation. And we have that the Wigner kernel of T is given by applying the Wigner transform composed with a linear change of variable to the Schwarz kernel. And we have this relation in terms of time frequency concentration of the two kernels. And this holds for every p between 0 and infinity. So now we can introduce our class of Fourier integral operators. So given a symplectic matrix S and Q between 0 and 1, an operator, a linear continuous operator from S to S prime belongs to FIO of S M infinity Q if its Wigner kernel satisfies this relation. And we have the algebra property of this class. And now I will give you idea of the proof of this algebra property, which will be fundamental to prove that propagators satisfy and join this class's property at every time. So first we see that operators in this class are bounded linear operators on L2. The first step is to use the algebra property of pseudos, which allows us to say that sigma, which has kernel H, the notation are the same of the definition. So sigma is the pseudo with kernel H. And it is bounded on L2 for the algebra property of pseudos. And then the operator capital K with integral kernel K satisfies this relation. You can obtain it with a straightforward calculation. And so it is, of course, linear bounded operators on L2 of R2D. And then we simply use the Moyal identity and interwinding relation between K and Wigner distribution to obtain the continuity, the boundedness of T on L2. The second property is more technical, so I will jump to the third property, which is which tells us that the inverse of an operator in this class is still an operator in the class FIOS of S minus 1 M infinity Q. We first proved that the adjoint is in the class FIO S minus 1 M infinity Q, and the key idea is that its Wigner kernel is obtained just switching the variable. And the second step is that T star and P equals to T star T are invertible. And by using the second point where you compose, which tells you that when you compose two operators in this class, you obtain another operator in the same kind of class, but the composition of the two symplectic matrices. And we discovered that P is in the class FIO of the identity M infinity Q. And so, by definition, the capital K of P, which is the operator at the time frequency level obtained starting by P, starting from P, is an invertible pseudo-differential operator with symbol in M infinity Q. And so we conclude just by using the algebra property of pseudos, and we obtain that P minus 1 is still in the class FIO of the identity M infinity Q, and T minus 1 is, of course, in the class FIO of S minus 1 M infinity Q. The main application will be to Schrödinger propagators, and we will see, we will give an in-depth look of how of why these propagators are in the FIO of ST M infinity Q, where ST denotes the Hamiltonian flow of the classical obtained by the classical problem. And this theorem tells us that this representation holds at every time t, and we have a better localization around the manifold Z equals to STW, which is what we expected to obtain from a physical point of view, because this linear subspace describes the classical trajectory. So according to the correspondence principle in quantum mechanics, you expect to have a good localization around this classical trajectory. So the key ingredients of the proof of this theorem are these. The first step is to prove that there exists a sine t greater than 0, which is the same sine t I mentioned before, such that the propagators can be expressed as a type 1 Fourier integral operator for t between minus t sine and t sine. And Fourier integral operators of type 1 are in the class FIOS M infinity, FIOS T M infinity Q. And so the propagators are in this class for time belongs to this interval. And the final step is to use the algebra property to finally deduce that the propagators join these classes property at every time t, also in the caustic points. So this was what I wanted to tell you, and this you find some references about main works which are used in our work, also work by Mele Oliaro, where you can find similar techniques applied to other Schrödinger problems. So thank you for the kind attention.